Nice to see you. Well, to have you all back. Let me start by just recapping where we were yesterday. So just a quick review where we were yesterday. So yesterday we had discussed this problem of defining rough integrals. So we had this problem that we didn't, in the case where we were interested in, have a classical definition of this integral ASDWS, and in particular, so in the case where they're both C alpha for alpha less than a half. And but we were interested, of course, in solving differential equations in the case in particular for Brownian motion, where alpha is just below a half. And so what we then proposed is to solve or to define these integrals if for those A that arise naturally when solving stochastic differential equations by doing this kind of higher order Riemann approximation, if you want, of this stochastic integral. And so we then axiomatized sort of the ingredients that we need for this ansatz. So here this iterated stochastic integral, we just postulated what are the properties that we would like to have for that. So we call this thing boldface W, and we just give it a name and postulate what we would like to have. And the two key properties that we will see again and again in calculations today are going to be that we want to have an order bound. So in particular, so we wanted this thing here, as we let the T bar go close to T, that should have satisfy a bound of order 2 alpha. And for that, it was really important that you have here this recentering here, this base point dependence. And the other thing we needed to control in our calculation was this change of base point. So the base point here is this the starting point here in this interval, and we needed to see how it changes as we move that And the second main ingredient that we had, so what are our integrands? So with these A's that we can integrate now have this extra Gubinelli derivative, and I've just rewritten here the formula that we I mean, it's exactly the same formula that we had different yesterday. It's just that I've put the brackets a little bit differently. So I would want to interpret this that if I view the T as a running variable, if you want, for my A, then around any base point S, I can locally approximate the function well by evaluating A at the base point and then taking this kind of next order term in terms of this W, and then you get an error here of order 2 alpha. And the second thing that we wanted was also that if you want this derivative of A with respect to the W has also held a bound. And under these assumptions, so these were the only things we had postulated, we could actually check wait. Okay, wait, let's discuss this later. Let's discuss. We put this next or this second order Riemann approximation here, and showed that just based on the properties that we have postulated, we could just prove that this converge. And again, I want to stress sort of the picture of what I have in mind is what we say that if locally near a base point S, the A can be well approximated just basically in terms of this W, and we know what W integrated against this dW is, then we can give a perturbative sense to the integral also of A against dW, well, in this way, okay? And so then we had seen, well, but this was kind of just a wish list for this W, so where do we get this integral from? This still required a probabilistic argument, for example, so in our case, we showed with Ito integration how this can be done. And that will also, we will see it again, that for certain like polynomials in a Gaussian, we will still have to use probabilistic arguments later also in the SPDE case. And of course, I mean, this is now my conclusion of this discussion of rough path theory. And of course, this and much more can be found in many places in the literature, in particular in this book by Peter Fritz and Martin Heira. So I think this is just the recap of where we were yesterday. Perhaps just a quick question. Are there questions about this? Everything good? Any comments about anything from yesterday? Okay. Good. So as I already told you yesterday, the plan for today is to extend this. Basically, the main aim is to extend this idea from one. Oops, my phone lost. Sorry, my iPad lost connection. I don't know why. Okay, better. It's back. So the aim for today is to extend this to higher dimension, of course, ultimately in view of using this for SPDEs, not just SDEs. And I told you already, I will actually show you later the example that we will work out is this PAM, or this multiplicative stochastic heat equation, which structurally already looks very similar to the rough differential equation we discussed yesterday. So the kind of in which order, I will actually first do a bit of a recap of negative regularity of distributions. So this will be something we will need. So I told you already that we, instead of integrating a function against another function, the point of view that we will take here is really that we will want to multiply a function with an irregular distribution. It's a very similar, I mean, it's basically just a different point of view on a very similar operation. And in order to be able to do that, I have to tell you how I want to quantify what it means for a distribution to have a certain negative regularity. So we need to do that first. And then I will give you a version of the reconstruction theorem. And this will look, if you've already seen, for example, in works on regularity structures, or in lectures that you may have seen, if you have seen a statement, then this will possibly look a bit different. So I will follow here a point of view that I learned really in a joint work from Felix Otto, in a joint work that we did a couple of years ago on quasi-linear equations, and that was then extended later in this the further joint work with also with Jonas Sauer and Scott Smith. And the sort of the vocabulary and the presentation will actually follow this very recent survey article by Francesco Caravena and Lorenzo Zambotti. But I will then later link to how that, I won't do this today, but tomorrow, how this would link to what you would have seen in Martin's original paper. And I will develop this actually in a specific in the context of a specific example, which is just actually a classical question of when can we actually multiply a function of regularity alpha with a distribution of some negative regularity beta. And we will figure out that just like yesterday, the condition will be that the sum of their regularities has to be strictly positive. And you should really think of this as just a higher dimensional version of this Young integration that we discussed yesterday, right? So yesterday we had, I showed you as the first part of the calculation how to integrate functions against one function against another function if the sum of their regularities is bigger than 1. And you should really view this as the analog of that. And then as the last step for today, I will actually show you how this then looks in the SPDE context. I will show you what is the analog of this kind of this iterated integral that I added in the rough integration. What is the replacement for that I will have to add in the case of PAM? And yeah, so that's the agenda. I think it's a lot to do. So let's just go for it. So let's start perhaps with negative regularity. And this slide doesn't contain very much that you won't. I mean, I suspect it doesn't contain super much. What you don't. Why is this disconnecting all the time? Sorry about that. Okay, now I don't know, perhaps the Wi-Fi is not so good. I'm sorry. So so this slide doesn't contain so much information that you don't know. So let me walk you through it quite quickly. So this is just a reminder of like vocabulary. So I mean, okay, I mean, I suppose you will know that the test function, so the space of test functions, is just for me the space D of smooth compactly supported functions, and this distribution is just something that you can test against the test function and where you have some reasonable bounds. And of course, the standard examples for distributions are just L1 log functions, where you just integrate indeed the phi against the f. So that's the thing that you should always think about. So where you average your function against the test function. And the other standard example, which is not just represented by functions, of course, the delta Dirac, which just amounts to evaluating functions at the origin. again, I don't assume there's anything surprising on this slide, so let me just move on. But now the more interesting bit is how to measure regularity of such an object. And so of course, I mean, sort of the point of being a distribution, not a function, is that we cannot evaluate them at points. And what I mean, or what we were going to do by measuring negative regularity, is to measure by how much we cannot evaluate at a single point. Okay, so let me make this a little bit more precise. So I fixed some nice test function. Say compactly supported. You should think of it as in this cartoon. So you should think of something. Let's say support is of size 1, on a ball, say of radius 1, and the height is say also 1. And now this is something we're going to see again and again today. So let me just show you once we do this rescaling. So we kind of squeeze it here around some point x, which in my notation I put here at the bottom, and then I squeeze it to scale lambda. So which just means that kind of what was size 1 before around the origin is now size lambda around my point x. And at the same time, I make the function, I mean, if I squeeze this closer together here, at the same time, I make it higher here. So that's a lambda to the with a lambda to the minus d. And the prefactor is, of course, chosen exactly in a way that the integral over this function is preserved. So, I mean, I suppose you know that. So the integral is preserved under this rescaling. It's always the same. And of course, I mean, you should in particular think that there's this case where this function has integral 1. Then you should really think of integrating f against this test function as taking an average of the function f on a ball of radius lambda around the point x. And of course, if f is nice, let's say even continuous is enough, then as lambda goes to 0, then this just converges to f of x. Okay. So the idea again, as I have done here, that this just gives you an average of the function f on a lambda neighborhood of a point x. And so what we do now, so of distributions, of course, we don't know a priori what happens if we can always test against these phi x lambda because they're all admissible test functions, but we don't know a priori what we get as we let lambda go to 0. And in general, it won't converge because, I mean, we know we're not allowed to evaluate at points. But so these negative Hölder norms, the way we define them, just measure by how much things fail to converge as lambda goes to 0. Okay, so what we do is we take a sup over a suitable set of nice test functions, and then supremum over x and all small lambda, and we say that yeah, I mean, we look at this quantity. So what this just means is if we average, let me write this here, if we average our distribution, sort of, we take an average over a ball of radius lambda, then this should be bounded by lambda to the alpha, and think of alpha negative. Yeah, it's written here. Right, so what this means is I say for alpha negative, a distribution is of class C alpha, well, for this alpha negative. If I take averages over a ball, local averages on balls of size lambda, then this blows up like lambda to the alpha. Okay. Just as a remark that I have already for later, I mean, this is a variant of these Hölder-Bezoff norms, and other people may have seen different representations of this, for example, with little PDE blocks or similar things, but I mean, it's all very similar, very similar. And another technical remark I like to make is that there's actually a very nice lemma that gives you a lot of liberty, which tells you that you actually don't, and if you want to control this, you don't have to know this for all test functions. You can actually just prove it for a single one, and then the equivalent bound for all test functions actually follows automatic. And I'm going to brush this under the rug a lot in these lectures, but in kind of behind the scenes, one uses this actually quite a bit improved. And just as a nice example, so of course the delta Dirac here is a genuine distribution. And so let's just check which regularity we get. Well, that's very easy, because if we test, for example, against this phi lambda, then we just evaluate this at the origin, and so this means this blows up like lambda to the minus d. And so in particular, in this way of measuring regularity, the delta Dirac is of regularity minus the dimension.
Hendrik, can
Yes,
I ask
please.
a question? When you say that a single test function is enough, it's like one that a particular one, or absolutely any one would be enough?
It's actually remarkable that actually pretty much any one is enough. The only property that you need is that the integral doesn't vanish.
Oh, okay, thank you.
It's surprisingly strong. It's and it's not even super hard to prove.
Okay, yeah. This is in Caravena's, or
this is in Francesca in Caravena Zambotti's paper as worked out. Actually, also a similar statement was also in Felix and my original paper on quasi-linear equation in the appendix.
Oh, okay, thank you.
And I think we took a proof that came from a paper by Felix with Antoine Gloria, and I'm not sure if they invented the technique, but it's that's where I learned it. Okay, good. So this is what we mean by negative regularity, and let me just walk you through kind of a nice consistency check that that this is actually a sensible notion of regularity. So, for example, if we have a C alpha function for some positive alpha, say in the interval 0, 1, then the derivative better should be of regularity. The distributional derivative better should be of regularity C alpha minus 1. But if that's not the case, then we have kind of done something wrong. So let's just check that that's true. So we test this this function here, the derivative of this, the distributional derivative of f against this phi x. Well, by definition of what it means to be the distributional derivative, that's the same as just integrating f against, well, with a minus as against the derivative of phi x lambda, right? So this is just really just the definition of what it means to take the derivative of a function, of a distribution. Well, and now this is the standard trick that one uses. We use the fact that, well, the derivative of the test function actually has integral 0, right? Because the test function is compactly supported, and if you integrate the derivative kind of far out from, you start at minus at 0, far out to the right, you go to 0, so the overall integral is going to be 0. And that means in particular, you can smuggle in here any constant that you like. And the constant that I happen to like here is f of x, okay? So I mean, again, this is really a very standard trick to smuggle in such an f of x. And now you see that this is nice, because now after we have used this cancellation, we can actually put absolute values and say that here we use the Hölder regularity that we had postulated. So we had to use it somewhere, of course. And then here we pull it out of the integral, and then we see that we only have to calculate the L1 norm, if you want, of this derivative of the test function. And the derivative of the test function, it's of course explicit, it's with a phi prime, but we have an extra minus 1 here from the fact that we've taken a derivative. So now just plugging all of that in, you get this lambda to the minus 1, I've pulled it out, this f to the alpha, I've pulled it out. Here I have this y minus x to the alpha. Here I have a lambda to the minus d times that. And now you see that this is just another test function. So the integral is going to give us exactly this. This is just going to give us a lambda to the alpha here, right? So this is an average, if you want, of this function here over a ball of radius lambda around x. So that's going to give us a lambda to the alpha, and we have exactly what we want. Is this calculation clear? So I hope.
Yes.
I hope I've convinced you that that this is somehow a sensible notion of regularity that we're going to work with. And perhaps the next interesting test case to check is what's the regularity of white noise, because white noise is really our prime starting point for everything. And there we go back to the scaling calculation that I've showed you yesterday. So so the scaling was, we had seen yesterday that if we, it's actually by definition just, so we want to, let's take the typical magnitude of the white noise averaged over a ball lambda here. Well, by definition of white noise this just gives us the L2 norm of this recentered object, the L2 norm squared. But then, I told you already earlier, the scaling is made such that the L1 norm of this object is preserved, but not the L2 norm. So I'm just making this explicit by just writing what this is. So this is just this lambda to the minus d1 you put in here, and the other one you put here in front. And then this one here disappears by scaling, but this one here stays. and you get a lambda to the minus d. And now if you take a square root of both sides, so this tells you that you would expect the typical magnitude of this quantity to be of the size lambda to the minus d over 2, right? So this suggests that this white noise has regularity minus d over 2, which of course is consistent with what we, at least in the one-dimensional case, we have just seen. Brownian motion has regularity just below a half. White noise we had seen is a derivative of Brownian motion, so regularity minus a half sounds about right. So there's actually a small subtlety that we really want to get a bound on, say, expectation of a norm. So this would be the expectation of this norm squared. But for this norm, the soups are all under the expectation, whereas what we have just got in our calculation was the soup sort of outside of these things, right? We have just calculated this for any given value of x, phi, and lambda. And this is, of course, very much reminiscent to something that most of you will have seen in the context of Brownian motion. If you go back to your first course in stochastic calculus, you will have seen that, I mean, you certainly have seen, or I mean, this is super, it follows from the definition, that for Brownian motion, you have this moment bound, that the typical size of increments is, again, that, I mean, t minus s, if you take square root of both, just like here. So the typical size in the sense of the variance of an increment over of length of t minus s is exactly t minus s to a 1/2. But if you want to really get the Hölder continuity of this thing, so the optimal bound that you actually get is that you actually get Gaussian moments for this Hölder semi-norm here with a small epsilon for any alpha less than 1/2. So what you have to pay a price, first of all, you have to work a bit more. So there's this, for example, you can use a version of the Kolmogorov criterion. And the other thing is that you always lose this epsilon, right? So Brownian motion, even though this calculation here would suggest that you have regularity equal to 1/2, typically, but then if you want to take soups there, you always lose an epsilon of regularity. So that comes here that you can only go to any alpha which is strictly below 1/2. And again, I mean, an extra argument is needed. And in this white noise case, it's sort of the same thing. You have to take a soup over all scales and over all test functions. And if you do this in the right way, you get exactly the same kind of statement. So you can get Gaussian type estimates for these local alpha semi-norms for any alpha less than minus d over 2. And I will not have time to go into how this is done, but it's really, so at least in spirit, it's kind of close to what one does for Brownian motion and the Kolmogorov criterion. Is this okay? Sorry for insisting a bit, it just makes my life, I mean, I feel a bit happier if people talk to me back. It's makes it more fun for me. So if you want to ask me a question, I like it. Anyway, so that's sort of now so much for negative regularity. So I hope that was sort of plausible. And now we want to move on to this issue of the reconstruction theorem. And I want to really develop it, as I had said before, in the context, kind of the higher dimensional analog of this Young integration that I did yesterday. So how do I get estimates on the product between a function and a distribution, okay? And let me just, as a warm-up, remind you of something that you may have seen on a course in functional analysis, for example, when you learned about distributions. You will have probably seen a statement like, I mean, if T is a distribution and G is actually a smooth function, then of course you can just define the product of the distribution times the smooth function by just putting the smooth function onto the test function. And if G is C infinity, then that's fine, because a C infinity function times a test function is a test function, and that's legal, okay? So in particular, if G is a polynomial, you're certainly allowed to do that. And then you will probably, as a next thing, have been told that, well, but if G is not a test function, then that's a problem, because of course, I mean, if G is not regular, then G times phi will not be regular. And so in particular, there's no, I mean, there's no way of multiply two distributions. And I think there's even a famous paper by Laurent Schwartz, which has this in the title. So this is I mean, I remember my first course on Schwarz distributions where this was kind of said very, very loudly that there is no meaning for this product of T times G if G is not smooth enough. I mean, of course, it doesn't always have to be C infinity. If the distribution is not so bad, you can play around with things. And so here I want to quantify that. Okay, so I want to show that if this is a C alpha distribution in the sense that we had just before for alpha below 0, and G is a C beta function for the sum, and I want to assume that the sum of these is positive, then this the product of these things is again a C alpha distribution. But I mean, it cannot be better than that because, of course, multiplying with a smooth function is not going to make anything more regular, at least not in general. I mean, as for example, multiplying with a very smooth function 1 shows. Okay, so that's the aim of the game. And let me perhaps start with a bit of heuristic, naive, how I can do that, which is aimed to remind you of what we've done yesterday in this derivation of this higher order Riemann scheme for the SDEs. So the quantity that we actually want to estimate, as I told you yesterday, is this quantity here in the red box, right? So we want to have this product, so T times G, which is still to be defined, but okay, let that not be our problem so much. So we want to know this product here, we want to average it over a ball of size lambda around some base point X, and we want to get get quantitative control on that. We want to say that that cannot blow up too fast, right? And so in particular, let's just write down some approximation for this quantity that perhaps it's legal to write down and that we could think should capture the main point. And the idea is, well, I mean, this is kind of an average around a point X. And near X, I could use the regularity of my G and could say, okay, sorry, let me just say before I forget, for now, both of the absolute values of alpha and beta are for now both going to be in the interval 0, 1. This makes my discussion a bit easier, and I will move to a more general case later. But so now I might think, well, I can use the regularity of G and near some, oh, sorry. When here you see my fabulous drawing of the smooth function G and the distribution. Sorry, this is much too regular for a distribution, but I cannot draw a more irregular distribution, so sorry about that. But you could think...
I don't see the drawing, I'm sorry. So the page is frozen.
Oh, wow, great, sorry. Let me just...
I see the slide with reconstruction theorem.
Yeah, sorry, thanks for pointing that out. I think my things, let me just stop sharing and share again, sorry.
There was also a question in the
yeah, so wait, let me just do the share again and then I can do that. Yeah, sorry, that's okay, so this is better, so I'm here. Okay, better?
Yeah, but perhaps can you try to answer the question? I think it was for the previous
yes, so let's go to the chat. Yeah, sorry. So
this should not TG belong to C gamma?
Well, what is gamma?
I think it's previous slide.
No, absolutely not. No, that C should not be dependent. Should not depend to C gamma. That's an important point. If you, well, I mean, think about it as a very simple counterexample. T is a distribution, well, whatever, your delta Dirac, and G is the extremely smooth function 1. So the product of those two things is still going to be the delta Dirac. So I mean, you don't gain any regularity by multiplying with the smooth function. But you make a very good point. What we will ultimately want to get is a bound on a quantity. We will want to get a bound of order gamma, and we will get a bound of order gamma, but not directly on the function T times G, but on T times G minus some counter terms. Does that answer that question? Okay, yeah, but I think Leandro had already actually answered the question in the chat. So thanks. Okay, good. So let's go back to what I wanted to say. So sorry that I think you may not have seen what I wanted to say. You didn't see my red box either. So I want to get a bound on this quantity, so T times G averaged on a ball of radius lambda around x. That's right, because that was what appeared in my definition of the norm. So let's see how we could approximate this quantity. And so if we want to say, let's say here's my point x on my drawing. Let's pretend this is my point x. That it seems perhaps sensible to say, well, near that point x here, my function g perhaps doesn't change so much. So g is close to constant. So perhaps I could actually approximate this t times g averaged over a ball of radius lambda. So think of lambda small, because that's what we're concerned with. We could probably have a sensible approximation by just replacing this g by a constant. We just evaluate that at x, and then we just test the distribution against we take the average of the distribution on that ball. Okay, so this is just, I mean, g is regular, so let's just replace it locally by a constant function. And this object, of course, is perfectly legal, right? So here everything is well defined because we take the average of a distribution over a ball. That's legal, we can do that. And then we just multiply it with g at that value. So this quantity is well defined, that's fine. And let's just do some very naive analysis of how big the error that we commit by doing that is. So the naive error analysis would be something like that. So if you just, I mean, I'm now doing all sorts of illegal operations, but think you're working on the level of a regularization where you're allowed to do everything. So then this Tg, this is the quantity we're interested in, averaged over the ball of radius lambda. So this is just this quantity here, right? So g integral of g times t against averaged around that here. And now we correct that with this quantity. So this was our approximation. And this actually has the same form, except that this g here, we evaluated at g of x. And now you see that this looks somewhat reasonable, that we might be able to get a bound on that, because here we can use again the regularity of g. So we would get a bound here of order lambda to the beta, because we're averaging over a ball where y and x are lambda close. And then from this average here, we would then get, I mean, this is not obvious that it's true, but it's plausible that it's true, that from here we would get this lambda to the alpha. So remind you that alpha is negative, and the overall exponent would be positive, and that would be the estimate that we get of order gamma, right? I remind you that gamma is the sum of the two. So this is the quantity that we will ultimately be able to prove that this has an bound of order gamma. And yeah, I mean, so it's plausible that it's true, but of course this proof is too hand waving. That's not legal, okay? Joseph, does this answer also your question? So this is the quantity of order of on which we will get a bound on order gamma. So for this object we're interested in, corrected by this naive approximation. Okay, and here you see also how you would get the gamma, because you can use the regularity of g in order to improve your estimate. And you see also that, of course, here for my stupid counterexample with a constant one, it doesn't contradict anything anymore, because the difference of these things is just zero. So the bound is trivial, but also not very, I mean, it's not very interesting, but it's still true. Then it's of course true. Okay, good. So that's the aim basically for the next few minutes, to justify this naive error analysis that this is indeed true, so that we indeed get this thing. And we want to start. We want to axiomatize a little bit these local approximations of distributions. Okay, and I'm going to do that here using vocabulary that comes from this this very nice survey by Lorenzo and Francesco. So they use they call it a germ, perhaps loosely inspired by differential geometry. So they call a germ a family of distribution which is indexed by a base point. Okay, so you assume it to be measurable, but not much. Okay, so so this is just a family of distribution indexed by base points. And what one should think of is really these fx are the local approximation of some target distribution. So if I imagine I want to understand what a distribution, in our case, the product that I want to understand, does near some base point x, then a good idea might be to just, well, make a good educated guess how it should look like near that base point x, when this is what this fx is going to be. And of course, ultimately, we want to show that, well, I mean, that you can go back to the original distribution just from these local approximations, right? And so yeah, the nomenclature, I'm always going to use the word base point for this variable x. And of course, going back to the example on the previous slides. So for example, there we wanted to approximate this distribution, as I said, the product t times g. And we just made this ansatz that that f of x tested against phi was just g evaluated to the base point x times the distribution tested against phi, okay? Let me just say that this vocabulary, the use of the word germ and also the word I will use on the next slide is not standard in the regularity structure vocabulary kind of literature, but I kind of like it, so I'm going to use it anyway. I mean, this is actually one of the most, I think, conceptually important points of the whole theory. So I think if there are questions, I think it's a very good time to ask. Okay, now or anytime. So the next thing is now the question, of course, that's going to be the statement of the reconstruction theorem that I will have in not the next slide, but the one after, is when can we go from such a local distribution? When can we get information from this family of local approximations on the limiting on a single global object? And in order to do that, it seems not implausible that one would need some quantitative control on the dependency on this base point, right? So, I mean, the base point was something we introduced artificially into our whole into the whole procedure. So we have to see sort of how things behave once we change that, and that's what this this norm here, the norm of germs, and this comes again from Caravena-Zambotti's paper. So they define this norm. Okay, so it's written here. This is a bit hard perhaps to digest. I think it's easier if you read it. For me, it's easier to read if I have it in this form here. So let me walk you through that a bit slowly. So what you do here, I mean, right, this expression here is the same, except that I have written the denominator on the right-hand side of the inequality. Okay, so it's really equivalent, except that I have a couple of soups and stuff like that here. But let me just walk you through this expression, okay? So first of all, what is the quantity you actually look at? That's already interesting. So we take this germ here and we evaluate it at two different points. Well, that's okay, right? So we had said before that that we wanted to measure the dependency on the base point. So that seems like a sensible thing to do. And now what do we test it against? We tested against, of course, a test function at scale lambda, but not anywhere. We tested only at one of those 2 points. I mean, of course, it doesn't matter if you put you tested at y or at z. So I choose to put it at y. Okay. So this is the quantity that we will need to control in our proofs. And what we presume, what we want is about, first of all, ignore this one here. That's just for scales below lambda. That's not so important. The most important one is this condition here. So for scales I mean, we're actually mostly for them where they're kind of equal to lambda. So for this situation, we get this blow up in lambda here. I remind you that alpha was negative. So so you do see a blow up in lambda of size alpha, which kind of corresponds to the irregularity, if you want, of the worst object. So but this is compensated by some sort of continuity in the base point, and it's compensated in the way that sort of the sum of these exponents is the gamma that we're ultimately wanting to have. Okay. So let me just show you this in this concrete example that we had before. So where we had this germ, which was defined by just evaluating this nice function at the point, which we could do, and then testing the distribution against phi. Well, let's just see. Well, okay, we take the difference of these two things and we test it around lambda. Well, of course, the difference between those two things that only sees, I mean, the difference only sees these different base points. So you have a g of z minus the g of y here. So this is here, and then you have just the distribution tested against your test function. And actually, it doesn't matter here so much for this calculation that this is evaluated at the same y. And now you see you're in exactly the situation which we kind of see by this norm. So you see here you get some continuity in the base point, which is given by the regularity, by this good regularity of the G. And then here you have this blow up of order alpha, which corresponds to the irregularity of the worst object. And so now, I mean, this is the power counting that I told you before. So gamma is equal to alpha plus beta. So you can rewrite it exactly in the form that we had in this norm, right? So gamma is some sort of yeah, the sum of all you should really think of gamma being, well, it is equal to the sum of the objects of regularities we want to multiply. So this is really a conceptual point. So I really would like a question on this one. Is this clear to everybody?
So may I ask a question?
Please.
So let me see if I get it right. So here you are saying that if you have a smooth function and a distribution, then you can multiply them if the distribution has index alpha bigger than -1.
Well, I mean, this -1 is I will address this -1 is convenient for me for my discussion now. That will be removed later.
Okay. Yeah, but
that's for me now. But I mean, the point is that, yeah, exactly. So I have I just need the sum of their regularities to be positive.
Okay. Okay.
But for now, I only want to make use of the Hölder regularity. But I mean, if you do this here, if you do this estimate here at the bottom, and if beta is bigger than 1, then it's wrong.
Yeah.
That's but I mean, of course, you can correct for that. But that's what I will show you later in the lecture.
Yeah. Yeah.
No, but the general statement is, and that actually follows from what we do today, is that you get very nice estimates if you want on generalized commutators for yeah. So yeah. And so you get very nice estimates. Sorry, if the sum of regularities is positive.
And also missed what was coherent in this.
Sorry, I didn't say that, and that's a very good point. So okay. This is vocabulary introduced by Caravena and Zambotti, is that they say basically if this they use the word coherent to say for one of these local descriptions, so germ in their vocabulary, that for which this norm is finite. Okay, that's just what they call coherent. Yes, Leandro.
Sorry, so I have also a question. So do you need to, well, maybe this will be addressed later. Do you need to already, because you want this from a stochastic point of view, you need to construct the coupling between all of those random distributions, or can you somehow look just at their at some dependency, like some stochastic condition, instead of having, do you need to construct the coupling between FZs? Because you suppose that you're in SPD, and I just know the law at this point.
So thanks. Actually, I forgot. Do you mind if I just still say one more word about the coherence from before, and then I try to say something, and then I can tell you if it's okay. So perhaps I wanted to just say something about the coherent word that Milton asked about. So yes, so this is a word that Caravena and Zambotti introduced, and I kind of like it, but it has and they say it was suggested to them by Massimiliano Gubinelli. But I want to just warn you that it's completely inconsistent with the language that Martin's group uses. So they have also used the word coherent, and they use it for something completely different and completely unrelated. And so it may be a bit confusing. And so I know when I gave a longer set of lectures on this, I kind of used this vocabulary, but I think I'm not going to use it very much here. So well, they use it, but okay, but it's at least inconsistent with what other parts of the literature do. And now the question about stochasticity versus coupling that Leandro asked. So, I mean, of course, what I'm doing here is just analysis, right? So there's no randomness anywhere in what I want to do here. And I think the flavor of this analysis, of course, what we're going to do later is these germs that we will actually have will include random bits, but very much in the spirit of what we did yesterday in rough path, the whole theory aims very much to separate probability from analysis. So you do need to once kind of get a good bounds on the objects that go in the construction of your germ, and that's very much like the construction of this iterated integral that we saw yesterday, that also has to be done using stochastic methods. But sort of once that is accomplished, I mean, it kind of localizes the probability in a single very clear spot, and once this is done, you kind of take this as an input and forget about probability for the rest of your argument.
So can you just look at some bounds on some moments based on the base point, and you can recover this? Does that make sense?
I mean, perhaps it's better. Do you think it's okay for you to, for the moment, just take this as a pure analysis fact?
Yeah. No, sorry,
and I will show you how this is used in the context of SPDEs a little bit in the end of today's lecture and a lot in tomorrow's lecture.
Okay, thanks. Sorry about
that. I think it's easier rather than me now giving some meta description of something. Okay, but I mean, so the point of this slide was just so we postulate we want to understand the product of a distribution of a function. We just postulate what a good local description could look like, and this postulate is of course based on our a priori knowledge of the fact that the function is nice. And then we define some norm which measures this dependence on the base point on these local descriptions. And so the main theorem I mean, that's kind of the analytical core of the reconstruction theorem is that if you have such a gamma alpha coherent germ in the language of Caravena-Zambotti, so this just means one of these local descriptions which does satisfy this, for which the norm that I defined on the previous slide is finite, then indeed there exists a unique distribution which is locally described by it, and is locally described in the following sense that so this is the reconstruction of this germ, and it satisfies this. So if you compare this with its local description and you take a local average of that around the same point, so what is important in this formula is that the base points here are the same, and you average this over some scale lambda, then you get an estimate that this is this decays like lambda to the gamma. And here it's very, very important that the gamma was positive. Okay, so I mean, in this dependency on the base point in this local description, we had this compensation between kind of the this nice factor with this x minus y to the beta, and this kind of compensated this alpha, and sort of here we get out of it what we I mean how much we have there. Okay, and f is called the reconstruction of f. So that's the statement. Now let me just this looks perhaps a bit abstract. Let me show you what this means actually in the concrete context that we had. So in the concrete example that we have, where let's just go back to f of x is was just given by just postulating, I just evaluate my function g and I test the distribution against phi. And we had seen that was the calculation method for this germ norm, or this coherence norm, is just controlled by the product of the C beta norm of g and this negative regularity T alpha norm of t. And let me just remind you, this exponent gamma was equal to the sum of alpha plus beta. And so this reconstruction f from the previous slide, of course, corresponds to the product g times t that we want to control. And so what the main point of this estimate on the reconstruction theorem is that, well, here's just, this is what the statement. So in this case, the left-hand side is exactly, well, here f times t minus phi x. This is just, so, I mean, sorry, this, or sorry, I'm sorry, this is g. Sorry about that, typo. So this f from the reconstruction, as I had said, is this product g times t. And I'm really sorry, this f is also a g. And so we compare this to the local description that we have here with this t. So this is exactly this difference here, and we average this around this here. And the right-hand side we had just seen is just given by the product of these things lambda to the alpha. And you see if you go back to the slide that I had a couple of in my naive error analysis, this is exactly the justification of this naive error analysis, right? So the estimate that I have here is exactly what I kind of said should be true. I mean, it was of course illegal to do this heuristics that I did here, but it kind of suggests that I get here this lambda to the beta, and I get here this lambda to the alpha, so this looks good. And the output of this is just exactly what I kind of in my naive power counting analysis at the beginning figured out it should be true. And there's another point of view that I want to also just mention here, which may be more familiar on this, which may be more familiar to you, which is you can, I mean, this f locally averaged against phi x lambda here can, of course, you can view this as just f convolved with some smoothing kernel at scale lambda. I think for this to be true, I think you have to change the sign, but it's not so important. And let's just call this f regularized at scale lambda. So this is what this curly thing here means, evaluated at x. And then the left-hand side of this identity, so what we have just here, can be also written as kind of the difference between the product regularized at scale lambda minus just the function f evaluated times just the irregular thing regularized, okay? And these kind of commutator bounds are actually objects that in harmonic analysis, or I mean, they are quite popular. So I mean, if there's, for example, and there's this famous Dupin-Alliance theory for irregular equation in fluid mechanics, and they use these commutator bounds all the time. So so this kind of estimate is actually something that in analysis is very famous, sort of. And it's also clear. Oh, now my thing disconnected again. Sorry.
Hendrik,
so I mean, this reconstruction theorem, I mean, at least as far as I've presented it so far, is really just a. I mean, if you want a slightly more axiomatized or a slightly more general version of these kind of bounds that are actually quite prominent or in analysis and in various branches of analysis. So certainly, yeah, I mean, certainly they have been in the literature like that before.
Hendrik, in the meantime, there's a question from the chat if the norm coherence, this norm depends on the test function.
Very good point. No, it's the same kind of thing as true that, I mean, in the way I defined it, I think I put a soup over all test functions, and I did. No, I did not. No, so I didn't put a soup over the thing. So I just fixed one. But it's the same kind of statement is true that if you have it for one, then you can construct an equivalent norm with another one. Does that answer the question? So you can basically pick one phi, or you can put a soup over all suitable phi in your thing, and you get equivalent norms. So no, actually, I think in the slides, I was actually there following the convention by Caravena and Zambotti, and I actually put just a single phi. I suppose I should assume some non-triviality, though. I think I should assume, say, integral of phi is not equal to 0. Otherwise, I think I would allow for equal to 0, which would give kind of boring norms. But that's the only condition that you need on the phi. Okay.
So, Henry, can I interrupt you a little bit more?
Please do.
Okay, so I'm just trying to understand this reconstruction theorem. Mm-hmm. So, okay, when you multiply by g, this is a very good example. Now, when you multiply by g, for example, the delta function is more or less clear what the delta function does. But for example, if you multiply white noise by a function g, this is slightly less clear because, okay, for me, if you think about the white noise as a stochastic process, then multiplying by g gives you another stochastic process, but it's do it pathwise looks a little bit more subtle. And can I understand this theorem as just the actual construction of that product between the function g and the white noise that I don't really know how to do?
Yes, I mean, I think definitely yes. But with this here, of course, you should think of as basically as if you think about the one dimension, this is sort of the case where g is nice enough. So you can, for example, if you wanted to multiply, for example, in one dimension G with a W dot, then if G has Hölder regularity a little bit better than a half, then you can do that deterministically. That's basically what this tells you.
Yeah, it's just because, you know, in a, for example, it's not clear for me immediately at least that if you do it stochastically, because stochastically, you know, I think that this is related to somehow to Leandro's question, no? Because you have the white noise and then you multiply by G, you can do it in L2 because it's a stochastic guy, but that does not guarantee at all that the new random variable is actually coincide with this guy pointwise, no? Because it's an L2 construction.
Well, I mean, I think they would coincide sort of as L2 objects, right?
Yeah.
I mean, sorry. Let me just rephrase that. So if you take, if you just take an L2G, then you can do it stochastically, but you can't do it my way because it's not nice enough. So for the thing to be legal for me, I need my G to be at least of class C alpha for alpha a little bit bigger than a half.
Yeah, but what I meant was okay. No, what I meant is that if you take white noise and then you multiply by a smooth function G, I know by just because of L2 theory, you know, of isometries, that this guy it's well defined and it has all the properties that it should have.
Yes.
But this is not clear a priori that that guy that I construct via L2 theory is equal to this guy that you are constructing deterministically.
But wouldn't it be true by basically both of them are constructed by some sort of approximation and it's the same approximation and they converge to, then they should also, if they both converge, then they should converge to the same thing, no?
Yeah, but then you have to use the reconstruction theorem to say that.
I'm not sure why you say that.
I mean, it's just that
I mean, I will show you in a minute how I prove the reconstruction. In particular, this is, of course, a construction. The existence of this is a convergence by approximation. And it tells you which object, converges to this F.
Yeah.
Oh, and you are.
I mean, my point is that at least for the derivative of Brownian motion, do it deterministically doesn't seem clear at all. I mean, it doesn't seem to be something that you just can do by hand, like in the case of the delta function, no?
But why not? I mean, Brownian motion is a C alpha function, and if and then you can take, if your G is nice enough, you can define the product of W dot times G. Yes,
I mean, you can define it, but I'm not saying, what I'm saying is that it's not immediate to do it, no?
But I mean, okay, not immediate in a sense, but this is what I just tried to tell you that you can. This is sort of a statement of what I've just done.
Yeah, exactly. But I mean, that's the point. It's a very powerful theorem because it allows you to tell you to say things that for me at least are not trivial at all.
No, I agree. No, I mean, I agree. It's different from the, it's in a sense, it's stronger than this L2 construction that you would do classically because of kind of, it captures, I mean, all these exceptional sets and all of that disappears. That's all of Sol. That's all kind of hidden in the fact that you don't want, that you already kind of, I mean, all the sets of measure zero and blah, blah, blah are kind of hidden in the fact that you want to control the alpha Hölder norm of W already, and you don't just view it as a family of random variables, right?
Right.
So the kind of the soup is already there, and the soup there allows you to then take, I mean, it gives you kind of a soup over all test functions, which are better than C a half. But I mean, I agree, it's not a trivial theorem.
Okay. Thank you.
But I mean, then on the other hand, it's also, I'm not saying it's not a trivial theorem, but it's also not something that certainly this kind of estimates has been in the analysis literature. These commutator bounds there have been around for a while. So there's another question about reconstruction theorem about Bonney's paraproducts. Yes, the answer is they are definitely related. And I mean, you may have seen that that there's this alternative approach to these singular SPDEs by Gobinelli, Perkowski, and Imkeller, and they use these Bonney paraproduct things in for exactly the same purpose for which I use the reconstruction.
Can you deduce these bounds on the resonant terms of the paraproducts from the reconstruction theorem?
On the resonant terms?
Yes, the one that's not kind of easily defined. No?
I thought, oh no, I think that this the reconstruction corresponds more to some commutator estimates that they have, which does of course give you these controls. So, but I'm not sure if you strictly logically can deduce one for the other, or if you just have to prove it with kind of a similar philosophy yourself. I don't know. But I mean, people have thought about this. It's just I don't know. I don't know exactly what they have proved. So
no, it's just that the exponents are the same for this resonant term, right? To be well.
No, that's true, and I mean, I would certainly view it as something very similar. And I think it's important that, of course, here in this estimate we get the sum of regularities, and that's of course the same as what happens in all these estimates in para-control calculus. That's very, very important. Yeah. Good. So thanks a lot for asking me some questions. Now I think it's actually a good time here to take a break, perhaps until 5:02 or so, for 10 minutes, and then we can reconvene. So, all right. So let's resume then. All right. So let's now that we have sort of seen what this reconstruction tells us in this very first example, let's perhaps discuss it a little bit further. So I want to perhaps first say a word about uniqueness. So the uniqueness proof is very easy, and it follows. I mean, that this condition clearly has to characterize this distribution f, and that's I'm going to show you here now. So let's just assume there were two such functions, such distributions f and g that satisfy this estimate. And of course, what we want to prove is that their difference tested against any test function psi is equal to 0, right? So that's the definition of being 0 for a distribution. And what we're going to use for that is, of course, the fact that, okay, I mean, let's first fix some small epsilon. And we're just going to do something pretty brutal, is we are going to just smuggle in this f of x, okay? So the difference between these things tested against this phi lambda here, think of epsilon, sorry, for phi epsilon, think of epsilon small, we smuggle in this f of x thing here, and we just do triangle inequality, right? So we take the difference here, and once we put the f of x here, and once we put the f of x here, and of course, now by assumption, this is going to be small. And here it's, of course, as you see immediately, this is only small if my exponent gamma is bigger than 0. And the other thing, so this is just by definition, right? So this is just basically the translation, a very straightforward application of this fact. And the other thing is a general fact continuity of convolution in the distribution in the topology of distributions is of test functions is just oh wow, this doesn't work at all today. I don't know why. Perhaps I have to move somewhere closer to the Wi-Fi at some point. Okay, sorry. Okay, so the other basic fact I'm going to use is some continuity of convolution in the topology of test functions. Is that if I test this distribution here, I mean, if I approximate the test function by just convolving it with this regularizing kernel, and then as I let epsilon go to 0, then this converges here. Okay, so these are the two only facts I'm going to use in the proof. But then it's pretty easy. So you want to just say, well, okay, I mean, this thing here is equal to the limit. So the thing we want to say is equal to 0 is the limit of this thing. But on the other hand, we can write this here by just putting this as the, well, putting this, just playing around with what this convolution actually means, is that this f of g evaluated by this thing tested against psi of x.
Sorry,
Sorry,
Sorry. I do not know what's going wrong here today. Yesterday we didn't have this. Okay. So you can just put this here as tested there. You use the condition that you have there. So this is bounded pointwise by epsilon to the gamma. And okay, then testing that against there just goes to 0. Okay. So the proof of uniqueness, it follows really immediately from this thing here that is equal to 0. And this says, oh, sorry, wait. So this says in particular the following. I mean, there's another quite interesting example here that I think is good to think about. I mean, what happens, of course, often, at least if you think about, you want to approximate some very irregular object, and you do it by something that is qualitatively smooth. So you want, of course, in the end of the day, to get estimates which are uniformly in your regularizing parameter, but at least in many situations, you qualitatively work with kind of smooth objects. You're actually allowed to write them down. And it happens quite often that this germ actually has this form that you kind of doubled that you have two variables, right? So it happens that this is not the distribution. You're actually legally allowed to write down a y variable and then really write this as this. So as a kind of something as a function with two variables, x and y. And I'm also always going to use the language that this is the base point as before. And for this y, I'm going to use the word running variable here. And so in that case, that follows from our previous, from what we had previously seen. Actually, this reconstruction does nothing but evaluating on the diagonal, because what we have just seen in the previous calculation is that this follows here, that this thing converges to if you smoothen this out in the y variable here, then it converges to the reconstruction. So the reconstruction is just, I mean, in general, of course, if you use this language of distributions, you're not allowed to say that, but at least in this qualitatively smooth setting, you should really think of this f of xy as something where you have artificially introduced a second variable. You wanted to approximate an object that had just one variable, and you have done it by introducing this artificial base point. And now you are, what is the output of the reconstruction theorem is the thing where you have put them together again, where the base point is equal to the running variable. I mean, this actually reminds me to a discussion that I had like a number of years ago with Milton in Oberwolfach, where he told me that he wanted to define the product of kind of irregular objects by just doubling the variable and evaluating it on the diagonal. And this is exactly what this does, right? So if you want to take this point of view here, this is what the reconstruction gives you. And my thing has disconnected again. I do not know why it does this every 2 minutes.
Should you try to maybe connect it as a separate account?
I should perhaps just do that. Yeah, sorry, let me do that. Perhaps that's better. Yeah, sorry. Wait, and sorry, I think I have the wrong meeting. Sorry. So if I zoom from here. Oh no, wait. So wait, I think I'm screwed up because I'm actually also somehow logged in. Do you mind if this is a bit complicated now? Do you mind if I just try it one more time and
Let's see.
Let's see if it works, if it doesn't want to work. Let's hope for the best for now, sorry. So what I wanted to just say is the reconstruction is you should think sometimes as these germs as something where you have artificially doubled the variable. So we wanted to approximate something that has just one variable. We have artificially introduced this base point dependence that allowed us to write things down. And what's the output of the reconstruction is just evaluating this back at the diagonal. In particular, if things are qualitatively smooth, then sort of by the uniqueness proof that we have seen before, the reconstruction has to give us the thing on the diagonal, okay? And this, of course, in particular tells us also that this gives you the sensible notion of a product that if you go back to this to the example that we had before. And this basically also tells you how you have to prove the existence of this thing. So we know that the reconstruction must satisfy that it's the limit if you regularize the test function here against this, which is just the same as just smoothing out here. I mean, it's right, really, you take this base point and then you average the running variable on a small ball of radius epsilon around x, and then you test that. And this is, of course, something that you can always define, and this gives you already something that has to approximate the limiting reconstruction. And that's basically how you always prove existence of this thing. So what one then does again is you go over dyadic scales and look at the difference of two things. So the proof is actually very similar in spirit to what I showed you yesterday for the Sewing lemma. But there are a number of different proofs now in the literature, and the difference always comes from the difference of this test function phi. So there are a number of technically different ways of doing it. So the original proof in Martin's paper used quite sophisticated phi. So this were kind of regular wavelets. And then there's this proof that I like very much that I learned from Felix Otto. And this is in our paper on quasi-linear equations, where we actually replaced this essentially by basically just solutions to the heat kernel at time epsilon, and then we could actually use the semigroup property of the heat kernel in order to go from one scale to the next. And then in some other work by with my PhD student Augustin Moinat, and then also AJ Chandra and Augustin, we kind of localized this and found a kind of a tweak on the semigroup proof that allows us to work with compactly supported test functions again. And then this proof by Caravena-Zambotti is, in a sense, it doesn't make any such like elegant choice of test function, and it becomes a bit more muddly therefore, but it doesn't use such a self-similarity property. And let me perhaps also mention this proof, which I kind of like. So this is somehow, I told you I gave sort of lectures of this type last year to some PhD students, and kind of as an assignment, I asked them to basically merge all these proofs in a single nice one, and they actually did this very nicely. So that's at the moment one of my favorite proofs of reconstruction. This was an essay for a course. I found that quite remarkable.
Hendrik is disconnected again.
I don't know. Should I make a 2-minute break and then I just try to set it up?
Maybe you could also use these slides online on your computer. I don't know if
yeah, but then I cannot point to anything, can I?
You can use your mouse. I don't know. It's just a suggestion. Maybe that doesn't work for you.
Let me just connect from the iPad perhaps, because I like to point to stuff. Give me a 2-minute break, okay? Zoom is not already set before. As I had already said before, I mean, in this treating of the product of G times the distribution T, I had sort of used the fact that the regularity of G that I wanted to use was not bigger than 1. Now let's see, because this is, I think, actually, I mean, it's highly instructive actually to do this, to kind of do the next non-trivial case where my regularity is below, kind of the absolute value of regularities is in the interval 1, 2. So it's kind of the next level of irregularity. And of course, nothing should go wrong. The threshold of absolute value 1 shouldn't matter, but let's see how it goes in the proof and what estimate one gets. So just setting that my local approximation, this germ, is just a product G times T is not enough, because if you do the same calculation as before, of course, you take the difference of these things. And then the best bound that you get on this increment of G minus Y, the G of X minus G of Y, is of course just, well, G is of course is more than C1, so it's Lipschitz, it's locally Lipschitz. So you can put here G prime and you have a Y X minus X, but that's not enough, because under this assumption, the sum of these two things is not bigger than 0. So that doesn't work. But I mean, let's just think about it. I mean, of course, we have also not used the full beta regularity of G. I mean, what we know is that we have a little bit more regularity than 1. And we're going to use this. So what is it? We're going to use this here again in this approximation. So we say Well, the quantity that we want to understand is this here, right? So ultimately we want to integrate, take the average of f of y times t, and then averaged over a ball of radius lambda around x. And the best approximation that we can find for this f of y is not just f of x, but actually the Taylor approximation, right? So we should actually we should do an approximation where we replace the f of x here by the Taylor polynomial of the first degree. And if we do that, then we get a new ansatz for this germ. So it's kind of a second order term. So we have the term that we had originally already, and now we have a second order term here with an f prime times this function here multiplied with a distribution. And let me just stress, I had said that before, but this is a perfectly legal operation because polynomials are smooth. So I'm allowed to multiply a distribution with a polynomial. That's fine. Okay, so that's okay. So this is a perfectly legal ansatz for my to approximate this product. And okay, I mean, I've not said it yet, but I mean, of course, I'm presenting things in a way to resemble as much as I possibly can the rough path calculation that I did yesterday, and also the calculations for the SPDEs that I will come to in the end of this lecture. So now let's use this ansatz and check the coherence condition, right? So we now set this germ here, f of x, here's this just replacing f by a constant term, and here this using the Taylor approximation thing. And let's do the calculation. So we want to compare this f at different base points, and we want to test it against this phi lambda. And now, okay, I mean, so from this term here, we already know what we get. We get here this increment times this term. And then for the next one, we cannot immediately write it quite in this form, because we have here, we have the base point x here. I mean, this thing we multiply with here actually depends on the base point. So you have an x here and you have a y here. So you cannot immediately put them together. And so now we have the situation. If you look at these terms, we already know, of course, that this term here alone is not good enough. And we know additionally that here we have somehow, I mean, we cannot even, we have to kind of do something to correct this this difference in the base points here. And of course, the hope and also the output of this short calculation will be that if we just correct for the wrong base point dependence here, we get an extra term which exactly cures what we need here. Okay. And I mean, I'll show you in the next slide. It's not a complicated calculation, but it's in a sense always a miracle, and it happens always in regularity structured rough path, and it's kind of neat. So the change. Let's first, just like yesterday for rough path, we have a change of base point formula, and it's a very, very simple change of base point formula. We can of course write this recentered product of the polynomial with t. We can write it as the recentered thing with at a different point. Right? And the only thing we have to correct for is, of course, the difference between the y and the x that we have just smuggled in. Okay. And let me just point out that this is all things I'm allowed to write down, right? Because here I have kind of an implicit argument, but this is just a number, and this is just a number, so I can multiply a number to its distribution. That's all fine, or a vector in RD. It's fine. I'm allowed to do that. Okay. So this is the change of base point formula, and I'm going to use this on the second term that I had before. So I remind you, I had multiplied f prime with this thing here, and then I had here the f prime of y with the thing with the other base point, and I'm just going to replace this one, the one with this base point here, by the one with this base point using this identity. And so what you get, I mean, it's not very complicated. Then for one, you have this t of y, so you get this product now with the same base point, and you get a second term which comes from this correction here, which is here. Okay. I mean, okay, I hope it was not a very complicated calculation yet. And now if you put this together, so we had already, this was, if you remind you of the previous slide, we had also another term, the one that we still had to improve. And I'm going to put the term from the pink square here. I'm going to combine it here with this. Then that is going to give me exactly this extra term that I wanted. So this is exactly now the Taylor approximation, the first order Taylor approximation of the function f near y compared to f of y, right? So the extra term here, this purple term that came from the change of base point formula, has exactly helped me to get a better quantity in the first line of my calculation. And this other line that I have here now also looks good, because here you have now can use the Hölder regularity of the derivative of f, and I'm sorry, actually f should always be g. I think at some point, so sorry, let's just consistently say I'm not confusing, f is equal to g for now. So this also now, so this quantity now looks very good, because here we have again, sorry, do I have this in more detail? No, sorry, let's just do it here. So this is now the summary of this calculation that we have just done. So here we have this this first term, which just is the thing with the derivatives, and this extra quantity with a polynomial now at the same base point. And the other one is the one we had before with this extra term that we got for the corrections. Okay, and now you see the second line here now is super nice, because we know that this is actually now bounded really by x minus y to the beta. So this is exactly what it means to be of class C beta, is that if you locally approximate it by a Taylor polynomial, we get an error of order beta. So this is what we have here. And then here we can use the irregularity of the thing. And for the first one, we use here the Hölder regularity of the function f prime, which gives us a bound of order beta minus 1. And now what we just need is an order bound for this quantity, which is exactly one better than this t that we have here for this x. So I think I was going a bit fast. Is it clear? I mean, I think the calculation that I've done was not super complicated, but possibly I rushed it a little bit. Is it clear what I was doing?
Estimation of 2 is not so clear.
2. Sorry, so actually what I wanted to say is this 2 here is just bounded by this, and actually this line here, this was not very good, sorry, this line here bounds this one. So I suppose, let me just ask, so the things that are now circled in yellow, it's clear that this bounds the one above, no?
Yes.
Okay, so then the question is, why is this true? Well, I mean, from here, you get this term, and that's just the definition of the norm.
Yes.
And so here, you use the fact that f is of class C beta, and beta was in between 1 and 2, right? So
yes.
Here, this quantity is just a Taylor approximation of f this is a Taylor polynomial of f centered at x, evaluated at y. And you compare it with f of y.
Yes.
And that gives you an error bound of order x minus y to the beta. Right? I mean, if you take a function which is of class C, whatever, C anything, say 3/2, and you approximate, and that one way of saying that is something is of class C 3/2 is you say, if you locally around a point compare the function minus the Taylor polynomial. I mean, you kind of take a ball around a point and you compare on that ball f minus the Taylor polynomial of f of some of the right degree. If you evaluate this at y, then you should get a bound of order x minus y to the order of the regularity, right? I mean, that's what it means to be of class C beta, is that you can be approximated by a polynomial and you locally make an error of order beta.
Okay, thank you.
It's basically Taylor remainder formula or something like that. Okay, but thanks a lot for asking. Are there more questions? Is the arithmetic clear that I've made? I mean, this is an important point, and we will encounter that again later. Is that yeah? I mean, perhaps I come to that in a minute. So but the only thing that is now left to show is, so you see here we have the bound that we want. You remember that in all these calculations, I always have gamma as equal to alpha plus beta. So we get here exactly the correct kind of small quantity that compensates the bad blow up of this one. But here our small quantity is not quite so nice. I mean, it's still this beta minus 1 is still positive because beta is between 1 and 2, but we want to we have to prove that this quantity here actually doesn't blow up quite so badly as the original one. And I'm just going to show you a little bit of an argument why that is indeed true. So this multiplying with a polynomial actually improves our order bound. And this is like that. So is it indeed true that if you take the distribution, you multiply it here with this polynomial centered at y, and very important is that these things coincide, that you actually get a better bound? Well, yes, because by definition, this thing, that's what I told you before, means nothing, but testing the distribution against the thing where I put the polynomial here on the right-hand side. And now let's just draw what this thing actually looks like. So this is basically a proof by picture. At the lower half of the slide, I have the rigorous proof by formula, but I'm only going to show you the proof by picture. So the proof by picture is, this is my test function, my original test function, which lives on scale lambda around this base point and has height lambda to the minus d. And now you multiply it by this function here that is linear and is 0 at the base point. So if you take the product of these things, you get something that looks like this. But on the ball where this one lives, this only has size lambda. So you pick up an extra form factor lambda to the minus, you pick up an extra lambda here. And that's what you can harvest in your so this gives you a better order bound. It gives you a whole better lambda than you had before.
Hendrik?
Yes.
Should it be minus alpha in the penultimate line?
Let me see
The
where
t, there's a norm on t and minus beta.
Oh yes, you're right. You are absolutely right. That should be an alpha.
Minus alpha.
No, I think it's positive.
Yeah.
My alpha is negative, no?
Alpha is negative. Yeah.
Yeah, so I think it's correct. Alpha. But I mean, I'm not going to walk you through the proof at the bottom. It's not very complicated, but at least I hope intuitively you kind of see that this is a test function which kind of you gain an extra factor lambda by just multiplying with this. Okay. So that's sort of the proof that you get that this also works. That this also works in the case where I have to use derivatives of this beta, but it's really quite remarkable. The proof is not so trivial, and it was, I mean, it needed at least some non-trivial algebra to go to this next order. And what I want to do on this slide here and on the next is actually compare the calculation that I have just done to the one that we had in the rough path thing yesterday. And you will see, and I want to point out the big structural similarities here, which are actually the key of what I will also have looking forward now in the SPDE case in a minute. So the aim in the reconstruction was to get a quantity or get an estimate on this product f times t, and I wanted to calculate averages at scale lambda around x. And the aim in rough path here was to get a good estimate on these stochastic integrals, possibly for t small, and then you get the better analogy. And the ingredients that we had were, sorry, I mean, before my f was always called g, but so it has shifted, this changes name in the middle, sorry. So the ingredient that I had was an f and c beta, and so I'm now referring to the case where beta is in between 1 and 2, and I want to kind of state it in the correct way, the way we've used it in the proof. So we have for this f, there exists a function f prime, which happens to be its derivative, such that you can build a local approximation of f near the base point y by taking the base point, and then you have a modulation of the polynomial y minus x, and the kind of the, if you want, the Gubinelli derivative, I mean the derivative of course is given by f prime. This is just a complicated way of saying that you have a Taylor approximation. And of course, this derivative also had regularity. So the derivative is itself of regularity beta minus 1. So this was kind of my nice assumption on this f. And for the control, very similarly here, the nice object was the a. So for the a, we knew that we had a good local approximation near every base point. We had here the function evaluated at the base point, and then we had here this, I mean, now it's really the Scubinetti derivative, not the real derivative, and it's a module, it's to next order, it's a modulation of a given function WT minus WS, and that gives me a good approximation up to high order for this A of t. So a good approximation of this A on a ball, if you want, around S. And additionally, I also used that this derivative itself, the Scubinetti derivative, it also had regularity, okay? And the next ingredient that we had here was that we actually know, I mean, right, we know sort of locally near any base point x, the function f looks like a constant plus a multiple of this linear polynomial. And we know also as an ingredient that we can define this product of this local polynomial, of this polynomial times t. And the two ingredients we needed for the proof was a change of base point. So we needed to know that we can, well, I mean, it's much not a complicated identity. If we change the base point here, we can just replace it by another one and we get an extra term that just corrects for these things. And we had this order bound, which told us that by recentering here this term, it actually looks a bit better than just the naive irregularity of the t that we had, right? This was in the previous slide. So this multiplication of this thing tells me that locally around this point x, it's very important that these things coincide. I have here this better order bound, okay? And on the right-hand side, we had the same thing in the rough path case. So we had sort of, we wanted to kind of integrate A against the dw, and we knew locally that near any base point S, the function A looks like a constant plus a multiple of this Brownian increment. And we also knew that we had sort of postulated that we knew how to integrate these Brownian increments against Brownian motion. And we had the same ingredients. We had a change of base point. That was this Chen's identity that we saw yesterday. And we had an order bound, which had the same property that we had that we get a bound here of order 2 alpha. So you remember the original irregularity of the dw itself should just be of order alpha, but because we have evaluated here at this S point, we actually gain an extra alpha here, right? So it's sort of from the regularity of the thing that we have here. So it'll just like from the smallness of this term here, we gain this extra one. So these were the ingredients that we had for the construction. And then for the reconstruction, we made this ansatz that, well, this locally around this point x, this should look like this second order approximation, if you want, which involves this derivative. This was the thing that we just put there. And in rough path, we did something very similar. We said kind of, at least for small times, this should look like just this high or the second order ansatz where we have just yeah, I mean, basically applied this integration to the local approximation. Okay, and the estimate that we get in the end, the final result is that the error that we make in this approximation is exactly given by sort of the regularity of the f, the bound of the nice, the estimate for the nice f with the worst term here. So kind of, I mean, the estimate that we have here with the correction coming from the change of base point from here, multiplied by the irregularity from here. And then the same thing here, and then you get the irregularity from here with the irregularity from here. So that's here. And here was the same. So we get sort of this lambda to the beta plus alpha corresponds to this t minus s to the 3 alpha here. And you have here sort of a regularity estimate from A. And again, this needs this extra term that comes from the change of base point from here times the norm that we get from here. And then here in the second term, you get a regularity estimate from here with a regularity estimate from here, okay? So the structure of things is really very, very similar. I think I made the case. And perhaps just a good exercise for you if you want to. Of course, the calculation that I've done here for multiplying C alpha and C alpha distributions with C beta functions, of course, doesn't only work for absolute value of regularity below 2. You can replace it by anything you want. You just have to make sure that you put enough derivatives here, and it's perhaps a good exercise to just do this for higher order expansions as well. So this is the end of my discussion of kind of this, if you want, the higher dimensional Young integration, the product of functions and distributions. But I think I've set the stage already so that it won't be too difficult to extend or to also include random terms. But before I do that, now in the last 15 minutes, is there any question? Look in the chat, there's something. Ah, no, that was something else. Okay, good. All right, so then let's move on. We have 15 minutes to go. Let's finally go to solve some SPDEs. So I want to now go to solve this PAM equation I told you, and in particular I want to give a meaning to these irregularities. And I want to just kind of before I go to that, I have to just, in order to not tell too many lies, I have to just introduce some quick notational thing. So in parabolic, now we're in the world of parabolic equations, and we're always going to measure regularity sort of in the natural scale for parabolic equations. So time and space behave a bit differently, just because in the parabolic operator, you have just one time derivative and two spatial derivatives. And so it's natural to measure regularity with respect to this kind of scaled norm. So Hölder norms are always going to be defined with respect to this metric here. And similarly, regularity norms with negative regularity are going to be defined exactly in the same way, just by I mean, now averaging over a ball of size lambda, but with respect to this metric, which means that if you in the t variable, you have to put a rescale differently with a lambda squared, and you get a lambda to the minus d here. So that I just wanted to say quickly. And so let me just then also say that then this means that if you now define calculate the regularity of white noise in this scaled metric, then the same calculation that I showed before will show you this here. This is not a difficult exercise, but I would just hope you believe me. So this means that if you measure regularity in this parabolic way, then space-time white noise will suddenly have regularity minus d being the spatial dimension plus 2. So which means that in this power counting way, right, I told you before, if you're in an isotropic space, then white noise has regularity minus d over 2 minus. And now if you measure it in this anisotropic way, then time counts sort of for 2 dimensions. So the effective dimension of d spatial dimension and one time dimension is actually d plus 2 in this sense, okay? And the other property that I don't want to discuss very much here is that if you state it in the correct way in this metric, then the inverse heat operator, so solving the heat equation, improves regularity by 2. And I don't want to, I'm just going to rush through this a little bit. And I want to now get to the SPDE. This is still a bit of like warm up for what I actually wanted to come to. So let me be a bit quick. Let's perhaps quickly just walk through the naive power counting of this PAM, why these things are kind of, why this is the first good non-trivial example to look at. So let's look at this PAM in 2 dimensions. So PAM was the case where we take a white noise, which only depends on the x variable, but is independent of a t variable. And so this, it's a white noise sort of in 2 dimensions. So there's no dependence on the time variable. So this will have regularity minus 1 minus. And then, so I mean, then the product of these 2 things doesn't have a chance to be better than the worst thing. So let's say that this product would still have minus 1 minus. And then, so if the heat operator improves regularity by 2, sort of the best we can possibly hope for the U to have regularity 1 minus. And then you see that this just about fails to this, because then sigma of U won't be better. And then you cannot define this product, right? So this is just outside of the scope of what we have just done. We have just seen kind of the Young case, if you want. We can define classically the product between the function and distributions if the sum of regularities is strictly positive. And here we just about fail. So in this power counting sense, it's really just exactly like solving an SDE with Brownian motion, with driving Brownian motion. But we could actually also go, and we're not going to today, and I'll show you a little bit how it works tomorrow. You could also do this in 3 dimensions, for example, and then the power counting would even be much worse. So so then you would have a minus 3/2 here that would give you a plus 1/2 minus here, and then you have still a 1/2 minus here, and you see there's a huge gap. So there's a whole, I mean, the sum of regularities is -1, so you have really a lot a lot to catch up with. And I just make this point here to say, I mean, these techniques are not limited to these borderline cases. You can go much further in your expansions, but here you have to add already actually quite a few terms later. And the other interesting case here is that this multiplicative stochastic heat equation in this power counting sense, this is now one-dimensional. So the spatial dimension is 1, which means in the space-time sense, this psi has also regularity -3/2. So the power counting is actually exactly the same as in the 3D PAM. And this is in a sense kind of really, really striking. So the power counting for the 2D PAM is much better, much easier than the power counting for this one, which is in a sense the most classical SPDE that people ever looked at, right? So this psi is space-time white noise. This is exactly the kind of equations that were solved, for example, in the Prato Subject's book using Ito calculus. So this equation, if you want to, you can solve it using Ito calculus. And this equation here up here, which in terms of power counting is actually much better, you cannot, because here you don't have, I mean, it's just not white in time. So you cannot do anything. It's in a sense a bit funny. But anyway, so this is what I want to do now. And I want to show you how you can build a local expansion now for this, very much in the spirit of what we had shown, what we had done for the ODE in the case of rough path. Okay, so this is now going to be the just guessing what this expansion near a base point should look like for this PAM. And I think this is actually one of the most important slides of the whole course. So let me take a bit of time to go through it. Okay, so we want to guess what a good local description of U near some point Z0 should look like in order to then postulate a good approximation for this product that we cannot define, right? And so the first thing that one might naively guess is, well, let's just do as we did before and replace the sigma of U of Z by the constant, right? We fix some base point Z0, and we just pretend that near that base point here, the sigma of U is just constant, equal to the value here. Well, okay, why not? So this is actually very similar to something that in parabolic regularity theory, if you prove so-called Schauder estimates, it's the freezing of coefficients. So this is actually a very, very popular technique in PDE. So what you say is that this should be the leading order term here for this near U, and then you have something here which should be an error. And let me ignore the error for now. And so if you do this ansatz here, then what this suggests, this is just a number. So this suggests you should near this base point be able to kind of say that increments of this U should look just like this number here multiplied with increments of the solution just with the heat equation with this right-hand side, right? So I'm freezing the coefficients. I'm just pretending this doesn't depend on Z. I'm just solving the equation with this right-hand side. And this looks like a sensible guess for what a local approximation should be like. And then I'm going to now use this to build a better approximation. So I do this here by just a Taylor approximation. So the next order corrector that I should here, I just get a sigma prime of U times the increment of U. And here I'm going to plug in what my postulate, what I had before. So this should look actually like sigma times sigma prime. And you see again, it has the same form as the Ito-Šartonović correction that we had yesterday times this here. And now I want to multiply this with eta. Okay. So this suggests this, this slightly formal freezing of coefficient argument that if we want to give a good definition to the sigma of U times eta, a good local approximation, then a good guess would be to just here fix this coefficient and just multiply with eta, and then that's tested against my test function. And the next order correction should just be this. So I put this coefficient, which only depends on the base point. And then I put here this Z increment near the point and multiply that with eta, and that I test against phi. So this is the end of a 2-hour lecture. Now, this was a difficult slide. Can I have a question, please?
Is this like, because yesterday we had this integral and wanted to integrate some A against something.
Mhm.
Then we found out we only have to be able to integrate W against itself.
Yes.
And so now here we want to multiply something with eta, and we find out we just need to multiply Z times eta.
Yes.
That's the idea that this is.
That's precisely the idea. Yes, correct. It is exactly very much the philosophy. We want to say that locally near a base point, this function sigma of u is well described by just the constant sigma of u of z plus a modulation of this function z, which is something I will tell you tomorrow that we understand perfectly well. This is a Gaussian process, just like Brownian motion. We know everything about it. And so what I want to tell you is we will be able to multiply sigma of u with eta if we know how to multiply z with eta. Perfect, yes. Milton, are you saying something? I think you're muted. Because you're shining on my screen, but perhaps. Okay.
No, not really.
Oh, sorry, then perhaps just a mistake, sorry. Okay, good. So I hope this freezing of coefficient, how I have derived sort of that this would be a good approximation, would be sensible. So now let me, just like yesterday, give you the definitions that I need in order, what are the ingredients I'm going to want to postulate what I need to make this work, okay? So as we just said, so I need to basically, I need to just be able to define this object and have the right properties, just an analogy to this boldface W that I had yesterday. And let me just tell you what I want to do. So the stochastic data that I need to do this product is the Z here, of course, that corresponds to the Brownian motion that I had yesterday. And then I need this quantity, this product, which corresponds to this boldface W. And let me for now introduce some notation here. For now I'm just using it because it's much quicker to write that than this. It takes less space on the slide and it makes the formulas look less hideous. So this is sort of my shorthand for this object. And let me perhaps don't wonder so much yet why I use this odd notation. And so the only things I'm going to use here is, again, an order bound. And the order bound is now an order bound of order 0 minus, which corresponds exactly. So the Z will have regularity 1, and this eta will have regularity -1. And so by recentering things here, I can harvest this full regularity 0 minus to get a bound. So I mean, without the recentering, I would just get a bound of order -1 here. But with the recentering, these are the same base points, I have a chance to get a bound of order 0 minus. And I also want to have the change of base point formula. And again, this is just by kind of changing this here, that this is what I should have. Okay. And having something like that. So yesterday I called this a rough path. Today I want to call this a model. And this is following Martin's notation and that he introduced in his paper. And I'm almost at the end. I will come back to this and do this again tomorrow and with a bit more calm. But the second ingredient will be, I just want to show you already a bit panoramically. The second ingredient will be exactly the analogy to being controlled by Z. So I will want the thing I can multiply to say that locally I look like, well, the increments of that look like increments of the Z. But I'm going to have to add an extra term here, which is kind of a polynomial, and I will discuss this tomorrow. And I will have, again, continuity conditions also on this coefficient. And perhaps the last thing I want to say, and then I will stop, is that then we will use this again to make this ansatz. And the thing we can then check, and it will be exactly the same kind of calculation that we have already seen today and yesterday twice, that this will indeed be coherent under these assumptions. And I will not attempt to do that calculation in 1 minute. I will perhaps stop here and actually go back to this definition tomorrow as the first thing. Are there questions? Was this last bit?
I have a question, Hendrik.
Please, thank you, Milton.
So this freezing of coefficients, does it always work, or it's it's a good idea to always do that first.
I'm not sure what you mean by always, but it's what's always done if you do regularity structures for parabolic equations.
Okay.
It's always this, yes.
Okay. Good.
I mean, it's not quite. I mean, the thing is that I mean, of course, the way it's written up is. I mean, it's not so explicit in the way it's written up in Martin's papers, but yes, this is what you do always.
Yeah.
Leandro, you had a question.
Yeah, sorry. So maybe now it's a better moment to because this was precisely what I was thinking. So if I want to construct some PDE, like do the reconstruction from it, and beside maybe I just have the law of the objects that I want to do, and they're all stochastic. For instance, say I'm trying to construct from these freezing coefficients, but I don't know, could also be with a quasi-linear equation, or like, yeah, doing some form of frozen coefficients. Can I just look at the laws to make the construction, or is there some, like, so actually, can I just look at bounds on moments of differences, or is this something like you mentioned yesterday about the fractional Brownian motion that under certain regularity, it just breaks, you don't have pointwise canonical construction anymore?
Okay, wait. So there's two things. So what do you do in practice now? And I will come to that a lot tomorrow. So, I mean, for the Brownian motion, for example, let's start with Brownian motion. So for Brownian motion, in this kind of way of looking at it, just as we discussed earlier with Milton, you want to see it as a Hölder function. So for example, you want to use some Kolmogorov theorem or criterion or something to really know that you have good control on a C alpha semi-norm. And then you view it basically as a deterministic object with some controlled C alpha Hölder norm. And this is the only thing that enters ever your analysis, right? So you really separate very strictly the analysis from the probability. So sort of once you have good control on the C alpha norm or moment bounds or something, you just plug it into your machinery and forget in that proof, you forget that it's random. And then in the rough path case I told you yesterday, so I gave you actually only kind of a second moment condition, a second moment calculation for the iterated integral. And then I told you can plug it into a deterministic machinery. And there I brushed a lot of details under the rug. So what you have to do in reality is you have to do also a kind of a 2-parameter Kolmogorov criterion, which tells you that you actually can again have a bound on the expectation of the soup of this thing over different T of S divided. So, right, I mean, you have to put the supremum under the expectation. And that is possible because it's a very similar argument to the Kolmogorov criterion. It's a little bit, it's not much more complicated. And if you remember for Brownian motion, what you use in this proof is actually very strongly for Gaussian random variables. You have an equivalence of moments that you can go from second to pth moments. And you use the same kind of argument. It's actually sort of somewhat similar to these concentration inequalities that Julian was discussing this morning even. So for Gaussian polynomials, you have similar concentration inequalities. And here it's really exactly the same thing. So you can show that the Z, the solution of the stochastic heat equation, is a function of regularity almost 1. And then you can again get a moment estimate. Then that I will show you tomorrow. You get a moment estimate on this or on this funny quadratic object here, on this quadratic object. And moments estimates you get probabilistically, and then you put it into some Kolmogorov machinery that tells you can put the soup under the expectation. And that again relies on getting high equivalence of moments and stuff like that to go to peak moments. But kind of once you have that, then you forget actually that the thing was random at the first place, and you just do deterministic analysis.
Okay. So if I do the heat equation for different frozen coefficients and I use this as the germ, the reconstruction is going to be the one with the variable coefficients then.
So I haven't understood that. I haven't understood that.
Sorry, so if you do Fz as the, oh no, there is a bit more to it, but if I take Fz as being the solution of the heat equation with a frozen coefficient at point Z, and then I try to reconstruct from this germ, is this the solution of the PDE where I'm allowing the coefficients to move? Does that make sense?
So you're basically saying, do you recover the classical solution by doing this?
Yes.
Let me discuss that. I think, well, the answer provisionally is going to be yes, but let me give a better answer tomorrow.
Okay.
Yeah.
Okay, thank you very much.
Are there more questions?
Hi, Hendrik.
Hi, Thierry.
Hi. I have a question. If eta was regular, I mean, the term, the yellow term would not appear, or what's happened in this case?
You can put it, it just gives you a better approximation. You see, what you get in the reconstruction is just this, right? The reconstruction F is just, if everything is regular, it's just the thing evaluated on the diagonal, right?
Mm-hmm.
That's what I said earlier. And then this term here on the diagonal just disappears because this is equal to Z of dot, if you want, minus Z of Z times eta. And then you evaluate this at Z.
Mm-hmm.
So it disappears.
Yes.
So in terms of the actual value of the reconstruction, it doesn't change anything, but it gives you a better approximation of the thing.
Okay. So there's still some object, even if it's regular, but you don't see in the reconstruction or something.
I think it's sensible to think of it as sort of, if you think in terms of numerical approximations of a higher order scheme, it doesn't change the limit what you converge to, but it does change the order of convergence.
Okay, thank you. Okay. Yeah. Thanks a lot.
There more questions? So then I think, are you, yeah, you're the chair, Anders, no?
Yes, okay, then let us perhaps thank Hendrik for his nice second lecture. And we then are coming back
tomorrow. But tomorrow we're swapped. Milton and I have to swap you tomorrow, no?
Yeah, for your lecture we are coming back tomorrow, but for Milton's lecture we're coming in at in several minutes at 15:15 UK time.
Okay.